Okay, thank you everyone. Well, welcome. It is our second virtual seminar series of the semester, so I'm glad to see all of you here. My name is Shauna Stoy. I am the graduate assistant for the CDRE. Unfortunately, Dr. Hagelgans and Dr. Yalda are both at meetings today, so I have the wonderful privilege of introducing Paul Benyetta today, who will be our virtual seminar series presenter on nuclear power generating stations. So just a brief bio for Mr. Benyetta. He has received his Master's in Science for Emergency Management as well as his Certified Emergency Manager, and he is also a Master Exercise Practitioner. Mr. Benyetta is a member of Adams County, PA, the local Emergency Planning Committee, a volunteer in Adams County Emergency Operations Center, and holds a Pennsylvania Emergency Management Agency Professional Certification for County Emergency Management staff. He received his Master's in Emergency Management from Millersville University in May 2013. In June 2008, Mr. Benyetta received an International Association of Emergency Managers Certified Emergency Manager designation. Mr. Benyetta has completed EMI's Master Trainer Program and Master Exercise Practitioner Program. Mr. Benyetta was the State Training Officer for the Connecticut Department of Emergency Management and Homeland Security. His responsibilities included coordination of all federally funded training programs for the state and conducted training in various emergency management topics for the State Department and municipalities. His duties also include coordination of statewide exercise programs. Before joining the Connecticut Department of Emergency Management and Homeland Security, Mr. Benyetta was the Emergency Management Coordinator for Manchester Fire Rescue EMS Department, developing and implementing disaster preparedness and response plans for the town of Manchester, Connecticut. He introduced the Community Emergency Response Team program to the community, developed a special needs database, and held the position of Secretary and then Vice Chairman for the Capital Region Emergency Planning Committee, and was also the Chairman of Emergency Support Function 16 and Chairman of the Capital Region Citizens Courts Council. Prior to joining Manchester, he was in the nuclear power industry for over 25 years. He held a U.S. Nuclear Regulatory Commission Senior Reactor Operations License for Millstone Unit 1. He was also the Assistant to the Unit 1 Operations Manager, Assistant Supervisor of Operations Training and Project Manager for the Program and Process Reduction Project for Millstone 1's decommissioning. Millstone Unit 1 was a boiling water reactor similar in design to the Fukushima Daiichi nuclear power plants. Mr. Benyetta served in the U.S. Navy, where he was qualified in submarines and engineering watch supervisor on board the USS Nautilus SSN 571. Prior to moving to Manchester, Connecticut, Mr. Benyetta was Vice Chairman of the Public Safety Commission in Montville, Connecticut for many years. And Mr. Benyetta also holds his amateur radio license called Sign K1PJV. So without further ado, I am going to introduce Mr. Benyetta, who is going to take away the presentation today. Paul?
Thank you, Shauna. Can everybody hear me pretty good? If you can give me a check. Okay. I guess that looks pretty good. And again, I'd like to thank Shauna for all the help that she's given me in getting ready for this. And thanks for that great introduction. I didn't know that my bio was long. Okay, as Shauna said, this was a presentation that I started to work on when I was with the Connecticut Department of Emergency Management. Connecticut had, at that time, 4 nuclear power plants. 2 of them are currently decommissioned, 2 of them still operate. So we did a lot of exercises on a regular basis. And although the DOC staff and the people in the department knew their portions of it, a lot of them didn't really have a background to understand some of the things that were going on at the plant as they were going through their exercises. It's hard to understand, so I kind of developed this one, this presentation, just to go on, and I've done it with Safe Connecticut, and I've done it with Adams County with our volunteer EOC staff, because Adams County is going to support communities for 3 Mile Island. So we also tend to drill on a regular basis, and we have evaluated exercises on a regular basis for 3 Mile Island nuclear power plant. This slide is 3 Mile Island. The plant over here is Unit 1 and the cooling tower is 4. Unit 2 is, excuse me, Unit 2 is here. Unit 2 is the back unit. Here in the cooling towers 4, Unit 1 is here, which is still in operation, and these two are the cooling towers 4. Now, the NRC currently has 100 licensed nuclear power plants in the United States. 65 of them are pressurized water reactors, similar to 3 Mile Island, and the other 35 are boiling water reactors, which is when I was originally licensed. Those plants produce about 20% of our nation's electrical use. The NRC also licenses, but it isn't too well publicized, 36 research reactors. And a lot of these are at universities. They're used basically for physics type testing, putting samples in and dropping them down in an area where there would be a high neutron flux. So just to test materials and things like that. I was going to say, if any of you have any questions, if you want to kind of write them, you can write them in the chat area, and then I'll try and get to them as we go through the presentations. Okay. This was my first reactor, if you want to call it that. I was back in the after end where the reactor compartment was, the compartment engine room, and I served back there for 3 years with the Nautilus, which now is also decommissioned and it's a museum. So if you're ever in Groton, Connecticut, you can go back there and check out the Nautilus. My second reactor over here was Millstone Unit 1. This was a boiling water reactor. This went into commercial operation in 1970. And again, before I left, we had decommissioned it, and now it's in the decommissioned state. This is Unit 2. This is a pressurized water reactor. The original designers were Combustion Engineering. And over here we have Millstone 3, which is a Westinghouse pressurized water reactor. Currently now, we only really have the GE boiling water reactors and the Westinghouse pressurized water reactors as active designers and architect engineers for nuclear power industry. The other two, combustion engineering and backup electronics, backed out the mix of designers. Just want to go through a little bit of basic atomic structure. Here we have our nucleus. We have 2 protons, the red positive things. The green are neutrons, and then our electrons, which swirl around it in the cloud, are back around it. Now, helium, which this is also called 4He2. And that basically goes, the 4 means that there's 4 things in our nucleus, the 2 protons and the 2 neutrons, and then the 2 is what's in our electron cloud around it. So as I go into this, you'll kind of understand why I'm going through this a little bit. This is our basic structure. Everything is sort of built on this, and there can be other compounds that form together as we go through it. On this slide, we're getting a little bit more complicated, but over here we have uranium-235. Uranium-235 is our primary material that we use in the power plants. Uranium-235, again, we have 235 things in our nucleus, and we have 92 electrons. So basically, that in the nucleus we have our 92 protons and 142 neutrons. And it is stable. Uranium-235 is a stable atom. To cause the fission process to occur, we basically, in the reactor itself, I'm going to show these as pictures in the slides, there's control rods. We remove the control rods. These allow neutrons, which are actually in sources that are actually in the reactor and then also part of the fuel once it's been irradiated. Neutrons will then be released. Control rods absorb, so they absorb them all. The neutrons will be released, and once they reach a certain energy, as they start to decay down, they'll interact with uranium-235. Uranium-235 will then become uranium-236, which is unstable. By unstable, I mean it wants to become more stable. It wants to go to a state where it can more readily exist. It will do that basically by fissioning. The fission into 2 separate particles, and then these 2 these two atoms, these two elements, actually glass. As they go, they're going to be what we call fission products. Okay, the process as we fission gives off our heat, our radiation, and everything else. Now, these two products, again, as the uranium-235 picks up a neutron, it becomes uranium-236. When we split, these two things here will always add up to a number of 236, depending upon what fission products we produce. There will always be the same number of 236 that we started with, but we can have 20 different products, fission products that are produced that will add up to that number. Also, part of the fission, we release anywhere from 2 to 3 neutrons as part of the split. So these neutrons that are released from fission go out, look for another uranium-235, and that neutron will cause this uranium-235 fission, produce 2 more, and those 2 more will produce 2 more, and basically that's our chain reaction process. Anytime we want to stop it, we just insert control. So it's a fairly controlled process, and I'll explain a little bit on some of the reasons why we're using it. And the neutron has to remain, or has to be at a certain level. So not all neutrons can actually cause the uranium to have fission. It has to be at a certain energy level. So that's where the control has to play, because they will absorb neutrons before they even get to this level of concentration. Okay, radiation. Our radioactive atom, as we talked about here, the uranium, it wants to become stable. The whole purpose of giving off radiation. It can give off radiation either as energy, or it can give off particles. When we give off energy, the energy is gamma radiation. Very high energy. Also, it's an electromagnetic type of radiation. It is pure energy. It's a wave. There's no mass involved. Similar to X-rays and things like that. Our particles that we give off are alpha or beta, and they have energy and mass. So they also have material that's going out that can be physically stopped a lot easier by other material that would the amount of material that we need for the energy. This is sort of a graphic that we've got our alpha. It can be stopped basically by paper because of its energy level. Beta can actually go a little bit deeper, but it can be stopped by the skin. And gamma is going to need reinforcement to take over lead or something called the mass of the lead. Again, our alpha, heaviest and most highly charged. They don't travel too far. They usually stop by paper or our bits and skin cells. The only area where we actually worry about alpha particles is if we ingest them. We either eat them, we drink them, or we breathe them. That's where we worry about it, because once they're in our body, we don't have the shielding outside of clothes, skin, things like that. Now they're inside, they are a lot closer proximity to our vital organ. So that's why ingestion of radioactive particles, as we'll talk about later, we'll see that as more of an issue. Beta are smaller, much faster. They can travel a little bit deeper through tissue, but usually they can't go far enough to reach our vital organs. So again, they're considered an outside body source. Again, beta is only considered a problem really if we didn't get it or get it into the other thing with beta for sources is when we did work, we also considered beta as an issue for damage to your eyes and cataracts and like that. That's really because you don't have a whole lot of protection for your eye. It can cause the lens of the eye is exposed. So for working in radiation areas, we would wear safety glasses, just your typical safety glasses, heavy type safety glasses can help with that. One little moment here. Is that any better, Sean? Or am I still breaking up?
Hi, Paul. You're still breaking up a little bit. Is anybody else having this issue?
Okay, is this any better? Okay.
It seems to be a bit better, Paul.
Okay, you're sounding a little better on this one too, so all right, we'll give this a try. Again, if you have problems, just kind of yell. I was talking about beta, and basically for beta exposure to the eyes, we really look at the safety glasses are really all you need to protect your eyes. Now we move on to gamma. Electromagnetic radiation, it's a form of pure energy. It can go through most materials, and it can travel great distances. These rays affect basically all human tissue and organs because they can go right to the body. Significant exposure to gamma can cause what they consider the radiation sickness symptoms, which is the skin irritation, nausea, vomiting, fever, hair loss, and actually burns in the skin. To shield it, we need basically things like lead, steel, and concrete rays, and also, for gamma radiation, and also for X-rays, because they're pretty much similar materials. And again, here's just the chart again. It just kind of shows that we've talked about alpha. It can be stopped fairly easy. Beta a little more penetrating, and gamma the worst that we have, and we need significant shielding to protect us from gamma. Okay, this is our first reactor that we're going to talk about, boiling water reactor. And this again is the General Electric design. This was the type that in Pennsylvania here we have it in Peak Bottom. That's a boiling water reactor, and it's also the similar type to what was used in Fukushima, Japan. So we'll kind of go over those in a little. All reactors, you'll notice, have got a containment structure. And we'll see this as we go through the slides. And outside of the containment structure, we have our turbine, which spins a generator to make electricity for the home, and our condenser. Now, you notice as I go through the slides that everything out here is pretty much the same. Doesn't matter if it's a boiling water reactor or a pressurized water reactor. The things in here, or things out here, are pretty much the same. Inside of our containment, we have our reactor vessel. These things here are our fuel and our control rods on the bottom. They're normally up within the core. We pull them out, and basically for a boiling water reactor, that's what I call boiling water reactors, we actually boil the water that is in the reactor. As it boils, it'll produce the steam. On normal operation, boiling water reactor is running around 530 degrees at about 1,000 pounds pressure. So we've got our 1,000 pounds of steam coming out, spinning our turbine. Once the steam is pretty much expended and there's nothing left to it, it goes into a condenser. The condenser really is just nothing but cooler. It's taking water from an outside source, and this outside source can be a lake, it can be an ocean, it can be a river, it can be a cooling tower. I'm going to go on with that in a little bit. Once we condense it, we basically take that water, we reuse the water, and we pump it back into the reactor vessel, and it oil goes back and gets close to the same cycle. The basic General Electric boiling water reactor kind of looks like this. This is the containment building, or secondary containment. This area in the center is the actual reactor vessel. And the area around here are all the pipes and everything that support it, provide cooling water flow through it, things like that. This structure here, it's hard to see, but you'll be able to see it in another slide. It sort of looks like an upside down light bulb. That's our primary containment. If we would have any type of breach in piping or anything, that would all occur in here. Now that's still inside of a building which has got a concrete outer structure. This sort of donut-looking thing underneath of it is considered the suppression chamber. Basically, if we end up with anything going on in here where we have a leak, it releases steam. The steam basically goes down through the pipes into here, and this donut contains, depending on the size of the reactor, when I was on it, contained 750,000 gallons of water. So that's what's going to be used for the emergency here. And we'll go on a little bit more and explain what happened in Fukushima. Let's see if some of these things like the suppression pool and okay, here's our pressurized water reactor. And this is similar to 3 Mile Island, similar to a lot of the other pressurized water reactors throughout the country. Okay, again, out here, basically pretty much the same material, same type of components. In here, we have our reactor vessel. Fuel is in here. Here we pull the control rods out through the top, and we heat up the water that's in here. Now, in a pressurized water reactor, we put up oil. Basically, all it's doing, pressure in this primary coolant loop is maintained at about 2,200 pounds. The pressurizer, which is just half full of water and steam, helps maintain it. So we have 2,200 pounds of pressure and about 530 or 40 degrees water running through this loop. The hot water runs out, goes through a steam generator. This is basically like a double boiler. It just boils the water. And the steam comes through. Again, this is somewhere around 1,000 pounds. So spins the turbine. The excess steam, the exhausted steam, is sent down to the condenser, which is then pumped back to the steam generator. So pressurized water reactors, we talk about two loops. The primary loop, which is just the radioactive coolant running through and cooling, and then we have the secondary loop, which goes out with the turbine condenser and back in. Here's a diagram of 3 Mile Island. Basically the same thing. You see we have our reactor vessel for we pump the water out to the steam generator. That fucking Wilcox design, like 3 Mile Island, is a little bit different type steam generator. That steam right in the top. Hot water right in the top. It was cooled by the cooling of the water coming up, and then we circulated that steam that went out of here, back to our turbine, from the generator, and went to our condenser, and maybe we'll get back in. Again, here's a pressurizer, and this just shows some of the valves in if they had an issue with some of these valves sticking or leaking, and we just had to diagnose that condition at that time. So basically, they leaked out and ended up filling the pressurized relief tank, and that's what caused the depressurization that led up to some of the issues that went on. PEMA uses cooling towers rather than river water or anything else. Cooling tower, basically, they take the warm water from the condenser that was used to cool the steam. They pump it in right the way up, and then it just sprays down, and it's cooled as it falls down to the bottom where that's collected. And here's another picture of the cooling tower. And I just kind of like to show this and talk a little bit about it, because after 3 Mile Island, cooling towers got a, they kind of became synonymous with nuclear power. They always show a cooling tower whenever the media talks about nuclear power. Cooling towers normally, if we look at the ones at 3 Mile Island and the ones at other plants in the country, can be anywhere from 400 to 600 feet tall. And all they really rely on, they're just a chimney. They're hollow inside. All they rely on, we spray the water in, and based on the difference in atmospheric temperature from top to bottom, cooler ground air goes in, gets heated up by the water that we're spraying in, and then goes out the top. This up here really that you see is water vapor from the water that's being sprayed in and then being cooled off as area that goes up. So cooling towers, they're used by nuclear power plants, they're used by coal-fired generating plants, oil-fired generating plants, and also they can be used by gas-fired generating plants. So they're not unique nuclear power. The 3 Mile Island basically got that symbol, and it's been like that since. And here's just another one that shows it. We've got a cooling water that comes in, sprays on top, it's condensed, and then we pump it back in this plant is near a lake, so we're using the lake system as an example. Okay. All of the power plants that we have in the country are regulated under Code of Federal Regulations, CFR, by the Nuclear Regulatory Commission. The Nuclear Regulatory Commission has one whole volume called Title 10 Code of Federal Regulations, and that's divided into multiple sections, all types of different parts deal with specific parts of the nuclear power industry. Construction of the plant is a whole chapter based on construction. We have a whole chapter based on licensing, what they have to do from the start to finish of the plant. Operator training, this is all of the training that the licensed operators have to go through before they can be actually licensed to operate the power plant reactor. That's all covered in the chapter on operator training. We have our containment criteria, and we'll talk a little bit about that on the design of containments, what they're built for, and things like that. We also have our emergency cooling system criteria. That's the criteria they use for all of things like the pumps that pump water back into the reactor to keep it cool. So, Code of Federal Regulations has everything pretty much laid out. It's a rather thick volume, and depending upon what part of the industry you're working with, you're going to be going into a lot of detail on that section. I want to talk a little bit about the barriers. There's usually considered 3 barriers to the release of radiation. Our fuel pellets are little things in here. They're a uranium dioxide ceramic type material. Those are inside the fuel clad. The fuel clad is an alloy type material that can withstand temperatures, radiation, things like that. The fuel clad or fuel pin is considered our first barrier for release. And we have our reactor vessel and the reactor coolant system, RCS. This is all the pipes that go around, so we go with the steam generator and back. That's all of that. That's considered our second barrier, is the reactor coolant system. Our third barrier is the containment, which is a concrete building, usually depending upon the location of it. It can be anywhere from 4 to 6 feet of reinforced concrete, and they also usually have an inch to a 2-inch thick steel shell inside of it. So you've got steel and the actual concrete barrier for the buildings. Now, containments, depending upon the size of the reactor, they are designed for anywhere from 40 pounds of pressure up to the one I was on was about 65 pounds of pressure. And that's the pressure they can actually withstand in here if they have gas. So if there were to be a leak in the coolant system, water would have run out, hot water would catch the steam, it would increase the entire pressure in here. But the containment is designed to maintain integrity and keep everything within the containment. Doesn't really show here, but I'll show you some diagrams later where they show it. But there are going to be valves that actually penetrate the containment with support systems to cool it. And again, if you remember back to the steam generators, they had a steam pipe that went out and the water pipe that came back into it. All of those penetrations for containment usually will have 2 types of isolation on it. They usually have what's considered an indoor isolation valve and an outdoor isolation valve. So everything that penetrates it, in an accident signal, it will shut. So our steam line, if we were to have an accident signal of containment, steam valves would go shut, the water valves would go shut, and our emergency systems would fit. Now, for these isolation valves, there's always redundancy in them. And like I said, there's 2 valves for every line. One of them may be powered by an AC motor. The other one in that line would be powered by a DC motor. So they're always powered. If it's powered by something other than electricity, it can be a fail-safe form. It can be a air-operated cylinder that would open the valve. Those are all spring-loaded. Basically, in an accident signal, all the valves are on containment are designed to make everything within the containment. This is a typical pressurized water reactor fuel bundle. And this came out of this is a picture of one that was a pressurized water reactor. There's 193 of these in their reactor vessel. It's considered 17 by 17, which means 17 pins this way, 17 pins this way, and then all of the pins have got fuel pellets inside of them, and some of the pins don't have fuel in it, they have the control on it, which can down, stop radiation. So that's a typical for the fuel bundle pretty much is. This is a fuel bundle out of a boiling water reactor being removed from the reactor during a refueling operation. All refueling operations are done below water. They're usually done below a minimum of 8 feet or 12 feet of water. So this thing has got 12 feet of water between the top of the water and the actual fuel bundle itself. And it will be moved underwater over to a fuel pool where it will be stored until it's going to be reprocessed and removed. This fuel bundle, as we see here, blue glow to it. That actually does happen. It's considered Cherenkov radiation. That's the electrons that are being emitted from the fission products in the water. They're actually going out and they're exciting the water right around it. And basically, the water, returning to a stable state, will give off the light. Now, radiated fuel bundles such as this are very highly radioactive. And once they're exposed to that, we can't basically handle them outside of water. They always have to be in water and shielded. The new fuel assembly, if you look at it, the new fuel assembly, it has not been irradiated. It has not been in the reactor for the cycle. Actually, you can walk up to it, touch it, and everything else, because when the new fuel assembly comes in, personnel will do inspections on them. And then they will be moved into the fuel pool or the loading in the fuel. So once they get irradiated, they're that way forever until they can be shipped off to the special process. Our worst case accident, this is kind of the argument, this is what is a lot of emergency cooling systems. Pascal, can you tell us why the U.S. is not building power plants anymore? Basically, to answer that, it's more of a public opinion type thing. There hasn't been any new plants that have basically started up since after 3 Mile Island back in 1970. With that, there was a big public outcry for it, so they stopped building them. Those that were under construction, some of them were completed and put online, others weren't. There was a few years back, there was a talk of a resurgence in the industry. A couple of utilities actually did look at, and I think we're making arrangements with the MSC to actually look at building newer versions of the boiling water reactor or pressure water reactors. But the expense is one thing because of the large size of them. They're very expensive in the $1 billion range, and with a lot of public outcry, it's hard to get them unless you've got to sort of set away from everybody, so you don't have the proximity. I hope that answered your question, Pascal. Our loss of coolant accident. This is our what we call the design basis accident. This is the worst case scenario. Then we have our core, reactor core, our reactor vessel, our steam generator, and our coolant loop here. The worst case accident is considered a break in one of these large lines, the biggest lines, the reactor with coolant. And they don't look at just like a leak or a seam split. They actually look at what we call a guillotine rupture. Basically, we're looking at a guillotine rupture, almost like a piece of the pipe. Let me kind of finish this thought and then I'll come back to you. It's basically a large section of pipe that almost fall out, and the reason it's the worst case is we have water pumping out of both ends of the pipe. So we are depressurizing and draining out the reactor vessel at a very high speed because we're pumping out of both ends. So the reactor depressurizes, dumps all of its coolant out. So in a case, that's what a lot of the emergency cooling systems are based on. They're based on to increase the complete depressurization to get it down, and then they've got a number of systems where they'll just blow in water at a very high rate of speed and very large flow rates of water, basically refill the reactor vessel, so that even if we had the plate break here, they would refill the water at least to this level of the plate vessel. So the reactor core would be flooded underwater. And they would just keep pumping the water into it, allowing the water to cool the reactor, and then come out the break, go back into what's called the DSF, which is engineered safeguard. So there would be pulled out and cooled. Now Matthias asked, do you ever think we will see smaller scale reactors for commercial power? The large scale reactors is a feasible option for nuclear power. No, they're not. There was talk at one time, and if you look at the unit I was on was 600 megawatts, and they went to build up to the 1,200 megawatts, basically double the power that I was on for the middle versions. They could make them smaller. There was some things that I saw about it, but I think just because of the expense, investment, and all of the requirements, I think they're still looking at pretty much a large size, just for the fact that all the requirements involved, all of the staff and everything else, I mean, working with the outside communities for it. But I think they're still looking at trying to keep them in the local sites rather than, your neighborhood little reactor power plant could be out in somebody else's backyard to keep them there. So it would probably be a better idea, but I think last I looked, they were still thinking of large scale power plants. Again, so this is basically our steam and everything we've blown out of the reactor. It's in there. The pressure in our containment go up to the pressure is considered. These are our systems we use to reflood. And basically what we look at, we've got a number of systems. Again, these are about half of the system. DSF building, there's going to be like two trains redundancy. We've always got one train off the emergency power supply, another complete identical set off the so we've got redundancy. If we were to have our break in the coolant line, the first thing that's going to kick in is going to be our accumulators. They're basically large cylinders, pressurized cylinders with nitrogen. They're full of water. And as the pressure in here goes down, they'll start to blow water into the coolant system, the reactor core, start to keep it cool. Another system that would kick in automatically is going to be our charging system. The charging system is a very high pressure, but it's low flow. This is also used for normal makeup for the sand system, actually for the system for regular basis. So the charging system is going to kick in. Again, that's going to be high pressure, fairly low flow rate. The next one that comes in is going to be our safety injection system. This is an intermediate pressure, but a lot higher flow. And you'll notice that charging and safety injection, aka suction off the restoration. This tank is laying down the water, pull the water out, and pump in to start reflooding the reactor, and the water will come out and go down to the exit side. After our safety injection, we have residual heat removal, and this is going to be the same thing, take the suction off the reactor storage tank. You can actually cool the water that it pumps back in here. It'll get cool. And the other system we've got, our recirculation system, you see that this actually takes suction off at the bottom of the containment itself. The purpose of this is once we have our leak, the water comes out, we're doing nothing but pumping water in. It's being fed up by the core, drains back out, goes into the sump, and we can take it out with the recirculation pump, pull it off, and then pump it back in. So this is the feature we would use basically to cool down the core if we had an accident. We just take it out of the sump, put it to the cooler, and back into the core. The other containment feature, again, this is all there are spray systems to allow it to continue. We have different spray pumps. They can take a suction of water off the storage tank, and they just blow water in, and there's spray headers around different levels of containment, regardless of spraying and steam release in the accident. And again, here we also have this containment recirculation, which will then take water out of the sump, all the steam condense through a cooler, and then spray that back in to help cool the containment structure itself down. So these are your methods that we use for containment cooling. Again, these are all redundant. If we've got two on each side, one is going to be powered by one generator, one by another. Again, here you can see the valves. Again, we have motor operators, one would be up, one supply, one off. The Code of Federal Regulations, the NRC, has what they call classification of emergencies. These are basically how the utilities notify surrounding population, the county officials, town officials, things like that, and also the NRC. So do you think nuclear power plants are through this scheme? And what does the Chris Anderson do? That's kind of a loaded question because I spent 25 years there. I didn't think they were risky. I think they're controllable. We can easily deal with it. So, I wouldn't have any problem being near one. And again, like I said, I work now with the county, which on a number of basis we've talked and visited 3 Mile Island. The Price-Anderson Act came up early on in the utility industry, and the intent of that was because of the damage to a plant and population out there. There was no way that the utility company's insurance would put the bill for a lot of events that were on. So the Price-Anderson Act was pushed through by Congress, and basically that provided a dollar amount from utilities, federal government, a whole bunch of other things that would bear the cost, burden the cost of an accident in the nuclear power plant. And sort of while I'm on that, part of every utility has to contribute a certain amount of money to apply every year for something to an accident like this. And a lot of that money goes into the communities right around the plant and the host communities. That money is used for training people, training the DOC staff, providing them with equipment that they would need for radiation monitoring, things like that. So the utilities don't really leave the locals out there to dry. They provide a lot of funding the utilities can use to support anything that would happen. I know when I was in Connecticut, we were one of the within the 10-mile zone. I'll talk about it pretty soon. And they provided training for us. They provided net material for us. They provided instruments to us. They provided a lot of things that, if there was an accident, we would need. And some of those things, I sent the money when I was in Connecticut as a public safety commissioner. Some of that money went basically upgrading and getting equipment, computers, and things like that for our DOC. So, even though they may consider it risky, they do put a lot of money back into the community. And they don't need a form of salaries, but also help the local emergency members. Okay, emergencies. We have 4 basic classifications. The notification of an unusual event is our lowest classification, and these are things, again, that the NRC wants to know about, and also the utilities, the local responders may want to know about. A unusual event is not really an emergency per se. This can be just notifications of the one. The usual event sent out if you have, say, a piece of equipment that didn't meet its test requirements, or a piece of equipment that broke. So because maybe that equipment was used as one of the functions for a phone or something, that notification goes out to the NRC and also to the local officials around there. Again, that can be almost anything that the utility was when I was out there, we had somebody out because one of the individuals came in the morning with alcoholic breath. They detected him. He failed the breathalyzer test, and so he failed his fitness for duty. So we had to send back and move with a little bit too much in him about to stay home. So the usual event is not common, but it does happen on a regular basis. The alert, this is usually the first notification that goes out that's going to start spinning everybody up. Once we get an alert, that means there's going to be a possible problem with the front. It can be a degradation in the level of safety. It can be a number of conditions that go on for it. And each utility has their own set of charts that they look at and identify what the alerts and get levels for as to like the equipment and things like that. And the alert will get the utility to start gearing up for emergency organization, and also at this point in time, most of the locals are starting to stand up for emergency coalition, their EOCs, checking out their instruments. So the alert is our first thing that we do to get ready for emergency. Site area is the next one. This is considered a little more serious on it. We're actually in this one looking at events in progress that occurred that resulted in actual or likely major failures of functions for the public. So here we're looking at, we've got things going on that are jeopardizing the plant. So we want to make sure that we get everybody ready with the staff. We're going to see what we need to do to basically keep it in safe and stable condition. So site area emergency bumps us up one notch, gets us geared up for a lot more emergency type conditions. And general emergency is our biggest. This is actual or imminent or damage with molten fuel. We may have releases during the general emergency that can be expected to exceed the guidelines more than the immediate site area. So this is the highest level there is. This is the one where basically all the stops are pulled out at this point in time. Everybody would be responding. The government would be here. They may have even been on that here before. But they're going to be the ones who are coming in for this. Now, also as part of all of these classifications, the EPA has established what we call protective action guidelines. And it looks at what has failed and what possible implications that would be there. And then they have guidelines as to what the utility and the surrounding population or the surrounding emergency management would have to do. Emergency planning zones, these are our areas immediately around the plant. We have the plume exposure pathway, it's an area of a 10-mile radius around the plant, and we have the ingestion exposure pathway, and this is an area of 50 miles around the plant. So these are the two areas that we do most of the training for. Again, like for 3 Mile Island, this is done for the immediate communities around it. In Adams County over here, we're within the ingestion exposure. So we actually do our training because we're in within 15 miles of the region. Some people think Fukushima killed folks of the nuclear renaissance. Do you agree? I'm pretty much going to agree because there hasn't been a whole lot that we've seen in there in promoting nuclear power since Fukushima. So it probably did. I don't see, unless there's some major issues with fossil fuel or things like that, if we have issues where they're actually good, or something with a lot of the issues with nuclear power and waste. So they come up with a really great way of getting rid of waste. Then we may see a resurgence of the industry. But right now, I don't have a whole lot of hope in bringing it back just because of some of the things that have happened at the and the results of it and publicity from it. We have our 2 EPZs again, 10-mile and 15-mile radius. And there are protected action guidelines for the plume area, which again is the area within 10 miles of the plume. These are the areas where if we did have a radiation release and some particles and gases and everything from the plant got out, we are going to take action to protect the people within that immediate area. The action could be sheltering in place, on the left side, close all windows, go out, and make sure we have air into your plant to evacuate. One of the things here is the evacuation. There are, usually within the phone books of the areas around the country, evacuation maps that you would know. In the case of Plymouth Island, we have one town that basically instructs them to come up to Adams County. They have to evacuate and we'll check the radiation. Bias brings up GIS comes in handy during this, and definitely, because you've got an easy way of identifying the areas that you have to take responsibility for. And GIS also has got all the input from local exercises. Now you know who's there, what their individual requirements can be. One of the other actions for this initial thing in my idea would be the distribution and use of potassium iodide. Potassium iodide at times has been a political and media issue where this is placebos and stop all medication. Potassium iodide is very specific and it's very limited as to what it can do. Back sort of up front, I talked about fission products and atom split. It goes into different atoms. One of those atoms that we get as a result of it is iodine-151, which is radioactive. It has a fairly short half-life. Means in 8 days, most of it has decayed off. But the problem with iodine-131 is it is iodine. It is very thyroid specific. Meaning that if we ingest the inhaler and get it into our bodies, it will go to our thyroid and we've got the element that basically lodge in our thyroid and it would damage the thyroid, which then controls a whole lot of other functions. The purpose of the potassium iodide is it's a benign type of iodine that if iodine-131 is released, we would take potassium iodine out. The iodine in there would saturate the thyroid. So now if you do get exposed to iodine-131, this element can't lodge in our thyroid because our thyroid is already full of iodine. So it basically would go to our bloodstream and would be eliminated routinely. And again, it may cause other damage, but it may not do any damage to the thyroid. So that's the big thing with potassium iodide is we're only going to protect the thyroid, and it has to be fairly soon after a reactor accident, because iodine-131 is going to produce the fission product, and again, it has to make it half-life. So, again, it's limited and specific. Is it true that reactors that cannot melt down? There are different ones that the utilities like Westinghouse and GE are working on that are basically the way their protection systems are done. They are pretty much self-contained and they don't need any backup systems. So for them to melt down would be pretty much an impossibility because of the way they're designed. I was going to talk a little bit more about that when it comes to the section on Fukushima. So if I don't answer your question when I talk about Fukushima, just kind of remind me of that if you will, Pascal. For our plume, then the next one we have is the ingestion. And these are designed to reduce dose from injection of ingestion to radioactive materials. And be a ban on approval. Here we're looking at more or less the farm areas immediately around the, that 15-mile